for momentum, energy and force. In the video 3, we discussed the intimate link between space and time. Delta tau squared equals delta t squared minus delta x squared. So if we take a coordinate system, let x be the space coordinate and t is time. And this is a light ray, x equals t. So if you consider a point here above the light ray, and if you consider a trajectory that connects this point to the origin. So this is a trajectory that is time-like. A trajectory where delta t is bigger than delta x. So these are trajectories of existences. What we consciously identify as existences. Existences of particles or things or information. They follow time-like trajectories. In case of time-like trajectories, it is always possible for you to find a frame of reference in which the trajectory is not moving. Then we discussed space-like trajectories. Trajectories where delta t is smaller than delta x. These are trajectories of simultaneity. What we consciously identify as present moments or now moments. A line on which particles, things and information exist together. In space-like trajectories, there is no frame of reference in which the trajectory is not moving. But there exists a frame of reference along that trajectory in which everything is simultaneous. This is how space and time are intimately linked. This is how symmetrical the connection of space and time is. Geometrically, there is no space and time. There is a single four-dimensional structure called space-time. In this video, let's look at how symmetrical is the momentum, energy and force within this four-dimensional structure. For velocity. Ordinary velocity is expressed as delta x over delta t. The three-dimensional notion of velocity. So it can be expressed as delta x over delta t plus delta y over delta t plus delta z over delta t. X, y, z are the components of the velocity, which can also be expressed as delta x1 over delta t plus delta x2 over delta t plus delta x3 over delta t. x1, x2 and x3 represents x, y, z. Or in short, delta x of I over delta t. I runs from 1 to 3. So the ordinary notion of velocity, v, can be expressed as dxi by dt. Or this is v's of I. This is a three-dimensional notion of velocity. If you look at four-dimensional space-time, this is x of I, the space coordinate, and this is time, and this is the trajectory of a system. So if you look at four-dimensional space-time, is there a more general definition of velocity we can reach at in terms of all four coordinates? This interval of the trajectory of this object or particle can be expressed as x mu. Mu runs over 1, 2, 3 and 0. 0 is the time component. Instead of using ordinary time, if we use proper time to derive definition of a velocity, it would be more general to all 4 coordinates. So we can define the 4-dimensional notion of velocity as use of mu is equal to dx mu over d tau. What is the relationship between this 4-dimensional velocity and the ordinary 3-dimensional velocity? So if you consider the first component of this velocity, use of 1. Use of 1 is dx1 over d tau, which can be written also as dx1 by dt times dt by d tau. So divided by dt and multiplied by dt. So dx1 by dt is v of 1. And what is dt by d tau? Delta tau squared equals delta t squared minus delta x squared. If we divide everything by delta t, delta tau squared divided by delta t squared equals 1 minus delta x squared divided by delta t squared. Delta x by delta t, this is v. So delta tau by delta t, or d tau by dt is square root of 1 minus v squared. So dt by d tau is 1 over square root of 1 minus v squared. Since this term is going to appear over and over again in our equations, we'll name this as gamma. So gamma is 1 over square root of 1 minus v squared. So u1 is gamma v1. u2 is gamma v2. u3 is gamma v3. What is u0 then? Is there anything significant about u0? Let's find out. Use of mu is dx mu over d tau. So u0 is dx0 by d tau. dx0 is dt because x0 is t. So u0 is dt by d tau. We know what dt by d tau is. dt by d tau is gamma. So u0 is gamma. These are the 4 velocities: u1, u2, u3 and u0. dt by d tau is 1 over square root of 1 minus v squared. Let's put back the speeds of lights here. dt by d tau is unitless because both t and tau are times. To make this side unitless, there has to be a c squared here. So gamma, which is dt by d tau, is 1 over square root of 1 minus v squared over c squared. For ordinary velocities, this becomes 0. Then gamma is 1. So for ordinary velocities, use of I is v of I. And u0 is 1. If we can define 4 velocities to a particle, let's look at whether we can define 4 momentums to a particle as well. So this is x of I, the space coordinate. This is time. And this is the trajectory of a particle from A to B. In order to talk about momentum and energy, we need to define an action for this trajectory. An action that is, in the first place, invariant under any coordinate system used to calculate it. Why is it? Well, it is because this is analogous to the shortest distance between 2 points in space. So if this is A and B in space, so this is your x1 coordinate, this is y1 coordinate. The distance between A and B is the distance between A and B, regardless of the coordinate system you use to calculate. So if this is another coordinate system, let's say x2, y2, so whatever the coordinate system you use to calculate the distance between A and B, it is the same. Why? Because it is the distance between A and B. Similarly, the action of a particle is the action of the particle. So it cannot vary depending on the coordinate system you use to calculate it. So that is one property. The second quality is the action must be always the possible minimum in all other possible transformations. There's one quality we know in space-time geometry that satisfies these qualities. It is the proper time. Proper time is invariant under coordinate transformations, and it is always the minimum space-time distance between the considered 2 points in space-time. So let's consider the proper time to be the action. So action is the summation of all delta taus. A equals summation of delta tau. It's a convention that we multiply this by a constant minus m. So multiplying by a constant doesn't make anything change. But to maintain the convention, let's do that. So A is minus m integral of d tau. What is d tau? So we know what d tau is. D tau is square root of dt squared minus dx of I squared. Let's take dt out of this square root. So it becomes 1 minus dxi over dt squared dt. So what is dxi over dt? It is velocity. So action is minus m integral of square root of 1 minus v sub I squared dt. One minus v sub squared. So this is the Lagrangian. So we can define 1 minus v squared square root as the Lagrangian, but the convention is we define Lagrangian as minus m times square root of 1 minus v squared. Minus m once again doesn't make any difference. So it's the convention. So momentum, piece of I. So if you remember our lecture 5, the definition of piece of I is partial derivative of Lagrangian with respect to q's of I dot. So piece of I is dl by dq's of I dot. So piece of 1 is dl by dq's of 1 dot. So this can be written as partial derivative of Lagrangian is minus m times square root of 1 minus v squared over what is dq1 dot. It is dv1. So differentiation of Lagrangian with respect to v1. So we'll write this once again as minus m d1 minus v squared square root. We'll write it as 1 minus v squared to the power half, differentiated with respect to v1. So when you differentiate this thing within the bracket as itself, it becomes 1 half minus m 1 minus v squared to the power minus half. And we'll differentiate what is inside the bracket. So 1 is 0. V squared is v1 plus v2 plus v3. When we partial differentiate this with respect to v1, because v2 and v3 is perpendicular to v1, these become 0. So the answer is 2 times v1. So multiplied by 2v1. 2 cancels off. So p1 is plus m. v1 over square root of 1 minus v squared. We know what v1 over 1 minus v squared is. This is u1. So p1 is m times u1. p2 is m u2. p3 is m u3. What is p naught? Is there a p naught that is m u naught? Is there anything called p naught which is equal to m u naught? Is there any significance of this? Let's check it out. To find out, let's look at Hamiltonian. If you remember lecture 5, the Hamiltonian is summed over I, q's of I dot, pi's of I, minus the Lagrangian. So in our terms, it is summed over I, q's of I is x of I dot, p's of I, minus Lagrangian. So it is summed over I. What is x dot? X dot is v's of I. And p's of I is m times v's of I over square root of 1 minus v squared. So we'll put it here. So m v's of I over 1 minus v squared square root minus the Lagrange. The Lagrangian is minus m times square root of 1 minus v squared. So this is equal to summed over I m v's of I squared over 1 minus v squared square root. Because this is minus plus m times square root of 1 minus v squared. To simplify this, let's divide and multiply this term by 1 minus v squared. So we get everything under one denominator, square root of 1 minus v squared. So this thing becomes m minus mv squared. This is mv squared. So mv squared cancels off. And the answer is h equals m times 1 over square root of 1 minus v squared. So what is 1 over 1 minus v squared square root? We know what this is. This is u naught. So Hamiltonian is m u naught. So m u naught is the energy. P naught equals m u naught. The momentum along time axis is nothing else but the energy. So as a conscious being, if you interchange your conception of x1 dimension to the time and time dimension to the x1, what would be the difference you will notice? What you previously called momentum on x1 direction will become energy. And what you previously called energy has become momentum in new x1 dimension. In terms of momentum and energy, the space-time is symmetrical. What about the force? If there is a four-dimensional analog to the three-dimensional force, Space-time would be mostly symmetrical under inversion of coordinates of space to time. So let's look at force. The three-dimensional force F of I is defined by d by dt p of I. Let's see whether we could define a four-dimensional notion of force as F of mu. F of mu is d by d tau, p of mu. So p of mu is m times u of mu. So f of mu can be written as m d u mu by d tau. This also can be expressed as m d u of mu by dt times dt by d tau. This is triviality. So what is dt by d tau? This is u naught, or this is gamma. So f1 can be written as m du1 by dt times gamma. So what is du1 by dt? This is acceleration along one axis. So this is ace of 1. So f1 is m times ace of 1 gamma. f2 is m a2 gamma. f3 is m a3 gamma. Is there anything called f naught, that is m a naught times gamma? Is there anything significant to call f naught? Let's find out. F naught equals m times du naught by dt times gamma. What is du naught by dt? Du naught by dt is d by dt. U naught is 1 over square root of 1 minus v squared. So du naught by dt is d by dt. This also can be written as 1 minus v squared to the power minus half. So when you differentiate this whole thing in terms of t, this becomes minus half times 1 minus v squared to the power minus 3 over 2 times the differentiation of v squared becomes 2v. And because we are differentiating in terms of t, not v, we have to differentiate v. So that is dv by dt. So this can be written as 1 over square root of 1 minus v squared into the power 3. 2 cancels off, and v times a. So f naught is m times gamma to the 4th times v times a. What is this thing? M times v times a times gamma to the 4th. Let's try to identify. For ordinary velocities, gamma is 1 and gamma is unitless. So for ordinary velocities, f naught becomes m times v times a. So f naught is ma times v. So what is ma? Ma is the ordinary force, f of I. And v can be written as dxi by dt. So this is force times distance divided by time. It's the time rate of the change of work. So it is power. F naught is all about power. F of I is mai times gamma. So this can be written also as m times a means dvi by dt times gamma. So m times dvi is the momentum. So f of I is all about the rate of change of momentum in terms of time. And F naught is the rate of change of energy in terms of time. So if you invert your conscious notion of coordinates, interchanging your notion of x1 with t, you will still perceive a world of energy, momentum and force without a problem. And also the same conservation laws will prevail. Subscribe to this video channel because this is going to be a comprehensive course on special theory of relativity. You can download this lecture note from the link given below.